Hello everyone, welcome to this video. In this video we shall see what is Fourier transform. So before getting to know what is Fourier transform, you should first understand why it came into existence and who gave it. So Sir Joseph Fourier, he was the person behind this Fourier transform, that he introduced this Fourier transform. So how did he get to this Fourier transform? He was studying the subject of heat transfer, where he was trying to solve his heat equation. So while solving this heat equation, he obtained the solution as the Gaussian function. So that means he obtained some functions of this kind, e to the power some quantities, say iota e to the power x or something like that. So there he got these functions. Now in order to obtain various conclusions about that, he used this Fourier transform, and in fact he developed this Fourier transform. So how can you define this Fourier transform? Well, this is a kind of integral transform. Now the integral transforms are the transforms which involve integration of some unknown function. Now this is your unknown function, right? You perform the integration of this unknown function, and where this quantity, that is known as the kernel. Now if you change the kernel, you have different kind of transformations. For example, you get the Laplace transform if you have the kernel. There we use the variable s instead of omega, so we have this kernel as e to the power minus st. If you have the kernel as e to the power minus iota omega t, then we call that integral transform to be the Fourier transform. So this is what we say, right? So how do we define Fourier transform? For defining Fourier transform, we use this symbol capital F, which defines the Fourier transform. So this is basically a mapping which maps the function f of t in the t domain. So we have some function f of t here in the t domain, where t represents your time, and that this Fourier transform operator, this shifts this function f of t to another domain, which is the frequency domain, and we obtain another function f of omega. Now note that in calculations and mathematical things, we generally denote the input function by the small letter f and the output function as the capital letter f over here. So this is the general expression that we are converting the function f of t into capital F of omega when we apply this Fourier transform operator onto it, right? So mathematically, how this operator is defined, you just replace this kernel by e to the power minus iota omega t. Therefore your Fourier transform of the function f of t, that becomes equal to integration from minus infinity to infinity. So now notice here that the interval of integration is the whole real line. So that means your function is defined on whole of the real line. So here we are saying the Fourier transform of this function is the integral from minus infinity to infinity of this function, so this is as such, into the kernel dt, right? And we call whole of this thing as capital F of omega. This is the notation here that we use. Okay, so after learning about what is this Fourier transform, so there is a question that can we always use this kind of transformation for any kind of function? Can we use such transformations? So the answer is no. Why? Because the given function, it should be piecewise continuous. Now what do you mean by piecewise continuous? That means it could be continuous within some breaks, right? So at certain points there should be only finite number of such points where you can see this discontinuity, right? So that should be finite in number. Those points should be finite in number. That means it should be continuous in pieces. And the second point here is that the function should be absolutely convergent. Now what do you mean by absolutely convergent? That means this should be a finite number. So that means whenever you take the integration of the absolute value of the function, then that should be finite. So that means we say the integral converges. If these two conditions are satisfied, we can then define the Fourier transform like this. So what is the process? So the process is that in most of the physical situations, our function is nothing but signal. What is a signal? So this is the sine signal, all of you know that. So we can also write the mathematical counterpart for this function f of t, which is the sine t. So here sine t represents your function f of t, and or basically what is this? This is some kind of signal that is moving around in the time, right? So I can use these two terms analogously. So that means whenever I'm calling function, that means I'm also calling this to be signal, or if I'm calling this to be signal, that also means function. So suppose I have a signal. What I do, I apply Fourier transform to it. So when I apply Fourier transform to it, what do I obtain? I obtain as a result superposition of sinusoids. So that means I'll obtain the combination of various sine and cosine waves, right? So what does this mean? So this means that you are now previously in the t domain. When you are applying this operator f onto the given function or signal, you are reaching to this frequency domain. So now in this frequency domain, you can perform a lot of calculations which are so easy to perform. What kind of calculations could be performed? It could be convolution or filtering or things like that. Now these are some detailed things, right? We will discuss them later on. So for now, you assume that we were initially here. After applying this Fourier transform onto this, we reach here. Now here we perform calculations, do manipulations, add, subtract, whatever we wanted to do, because here to perform some calculations, they are easy, and then we head back to the t domain and we got our answer. So this is the process. So what is the advantage of moving here? Why we are saying come to this frequency domain and it will be easy for you? Because here we use the sine waves, which are extremely smooth and they occur naturally in many situations. For example, you beat a drum. So whatever the waves they are coming, they are in the sine forms. Another thing is that sine waves, they could be added or subtracted so that they remains in the same frequency. However, the amplitude may vary, but the frequency remains same. So that is the beautiful property of sine waves that they possess. So it makes the calculation very easy. So therefore, we can say if the function is well behaved, by well behaved, I mean it should be piecewise continuous on whole of the real line, and moreover it should be absolutely convergent. So then we can perform this transformation from t domain to the omega domain without much loss. So once we are in omega domain, the frequency domain, we can perform these calculations, and once you have performed the calculations, you can go back to t domain. Now how to do this? How can you go back to your t domain again? For that you have to define another operator, which is this Fourier inverse operator, right? So this operator, when you perform this on the changed function f of omega, which you obtained after calculation, then you reach back to your function f of t. If you do not perform any manipulation, so you will simply reach at the function with which you started. So we were here in this frequency domain, so we applied this operator, which is the inverse Fourier transform. So we obtain to our function f of t over here, right? So we mathematically we say this function is defined whenever the input function. What is the input to this operator? This is capital F of omega. Now this thing should be absolutely convergent. If this is absolutely convergent, then we have this mathematical expression which says that whenever you wanted to calculate the inverse Fourier transform of the function f of omega, it should be 1 by 2 pi integration from minus infinity to infinity the same function f of omega. Now here notice that the kernel has changed. We are now taking a positive sign of this exponential term dt. So that means it is acting as the inverse Fourier of the Fourier transform that we have previously defined, right? So this is all about Fourier's transformation. We'll in the next video see some problems relating to that, and we'll also look at an interesting example where we can apply this Fourier transform. So I hope you understood this concept well. Well, that is it for this video. Thank you for